So we have this data collected from 500 households about how many smartphones they have. Would you recommend the company concentrate on selling data plans to individuals or families with 3 or more? And do you have evidence for that? Well, what could you do to support your answer?
Add all of them together and see which side has more. Like the 3 or more, or the 2 through 0.
What are we adding?
The numbers of people with active smartphones.
Okay, so by count. And it says there's 500. What else could you do? I mean, that's somewhat helpful. What did we do yesterday with our dice?
Do it over and over.
Oh yeah, we did. But percentage, right? Percentages are extremely powerful communication tools in math. I think the majority of people, probably beyond elementary school, at least have a somewhat understanding of what a percent means. So if we communicate things with percentages, it's probably more effective, right? So let's do that. Grab your calculators. What is it called when we turn these into percentages? Starts with RE. Good. Alright. Ready? Valeria, that's yours. Ryan. Cooper. Audrey. Gabe. Nate. Broly. Adam. Tom. I don't know if you guys can read this.
Yeah.
Jazzy. Corbin. And Jorge. That way we have some check. Everybody clear?
Yeah.
Alright. Valeria Broly, how about this one? Fail. We'll come back to you. Huh? Brian, Adam? Thanks. Guys, if you don't know what to do, ask. Cooper, Tom?
24%.
What was it?
24%.
Jazzy, Audrey?
28%.
Sorry, what?
28.8.
0.8, let's say 29. Gabe Corbin?
16%. 15.8.
So 16. Going back to this one will round to 14. Nate, Jorge? So 14 also? That can't be accurate. If this
No,
is 14, that
It should be
can't
around
be.
at
That one's
It's
13.2.
This one is?
Yeah.
Yes.
Okay, so what was this?
Yeah, 15.
They said 13.5.
Okay. Oh, I forgot the last category. Shoot.
Here, I'll do it real quick.
Yeah, thanks.
9%. I got
Something's wrong. Like these two are barely separated, and those two are like 5% different.
I got
So 44 is 8.8, right? So the highest rate. 37 is 13, or 66 is 13.2.
And this 37 is 14.
I got 0.74.
no. Yep.
I got 0.07.
So 7.4. Yeah.
So
And then you just have an F on one of them.
No, it's out of 5.
That was 9. 8.8.
No.
Okay, how about Valeria Broly? What percentage? 2?
Yeah,
2%.
I agree.
Okay. Relative frequency. Let's go ahead and briefly plot the distribution. And again, this is, because we're just doing single numbers, it's really considered categorical data instead of, so be careful with this. Gabe asked the question yesterday, can these bars be touching? That's for numerical intervals, right, where one runs up against another. That doesn't happen here. It's either 0 or 1. We don't have like a 0.5 of a cell phone. Okay, so it's really, even though it's numbers, it's categorical data. Meaning it's either one or the other or the other. What goes on the y-axis?
Our percentage.
Okay, so it looks like I need to get it maybe to 30%.
You can go like that.
Okay. I did notice, make sure that you're labeling your axes. Okay, so this is cell phones. And it's categorical, meaning there's no in between these numbers. So these bars need to be separated. Alright, so 0, we had 2%, it's a teeny tiny little bar. Will you guys just tell me so I don't have to look back and forth?
13.
And I'm not doing this perfectly, it's just going to be a little bit of a perspective. Gets harder the further over I go. Okay, so in terms of shape, you kind of see that shape. It's a little bit what we call normally distributed, where most of the data collects in the middle, with some out to the edges, but most of it kind of collects in the middle. Okay? If we did it like that. So, this company's maybe did what we just did, and trying to decide who they should market their phone data plans to. What would you guys say now? Okay.
Probably like from 2 to.
So 3 or more makes up how much percent of this?
A lot.
Well, let's do it. Like it's 16, 16, that's 32, and 29. 61.
Yeah, I got that.
So 61% of the data is here, and then over here, not nearly as much, right? Obviously, the majority of the data falls 3% and above, or 3 phones and above. But now we have mathematical proof of that, right? We're not just ballparking it. Does everybody follow? So you could go to your marketing team and say 61% of households have 3 or more phones. So what would that maybe dictate?
That they should market as marketed more for families of 3 than.
Yeah, like, you know, you see T-Mobile or you see Verizon commercials all the time, and now they're making these maybe more like family looking, everybody's enjoying their phone in a family instead of out hanging with the guys or whatever, right? Maybe something like that. So this kind of stuff is basic, but still illustrates how important it can be in a lot of sectors. Do you agree? Do you agree? I feel like some of you are like in space. Maybe we should do a space question, it'll reach you better.
Okay.
Go ahead and look up here. So they're all relatively the same scale, so that was the goal, so we could compare them. And as I scroll through, I want you to look at the shape of the distribution, which is like the green line that I just put on our warm-up. I know you can't read the numbers, but everybody scaled the the y-axis by 10, so 10, 20, 30 was the highest that any of these ever got. Okay? So what do you notice as we scroll through? Anything surprising? Do we expect them to all be the same?
No.
Why? I mean, isn't the probability the same for each dice roll?
Well, that's theoretical.
Okay, that's theoretical, right? So experiments don't necessarily reflect theoretical. Okay, now I want you to compare in each one, maybe we won't do all of them. What is the theoretical probability for this? So if I had asked you, theoretically, what should our distribution look like?
All of them being 1/6.
Do you guys agree? Yeah, they should all be the same exact size, right? Why?
Because the theoretical deal says that you have 1/6 of chance to get any one of them.
Theoretically, should any one of these pop up more than another? Okay. So I want you to compare each one to this theoretical standard now and see if you notice anything interesting. Number one, the first one certainly doesn't look like that, right? It's heavier, just like our cell phone data, it's heavier in the middle. I can't read that. Let's see if I can zoom it a little more. 20 something, 28% or something. Anyway, so keeping in mind what the theoretical distribution should be, what do you think? Look at that one's interesting. What about that one is interesting? Yeah, and the ones hardly got any, right? I mean, comparatively, it's low. Okay, that one had a low 2. That one had a couple similar low ones. That one was very similar across the board. 16, 16, 15, 15. So that was really close to the theoretical. In the theoretical, each one should be roughly just under 17. Okay? So, what should you take from this?
In like real life, they were not going to be exactly what they're going to be on the math test.
Okay, on the math test. What if the math test has this data?
Well, I just mean like theoretically, everything is supposed to be exactly like in a dystopian world. But like
In a utopia world.
utopias on the outside fringe.
Right.
But
So that's why it should be that way, theoretically.
yeah, okay. But like how we have it is more normal because
It's dystopian.
yeah, sure. It's dystopian.
All right, everybody go grab another die. We're going to do this for 5 minutes, just to prove a point.
What die?
Sorry.
Are we gonna record those?
I'll do it. This is just for illustration. Yesterday, everybody rolled this 100 times.
Or
Yeah, roughly, right? And you saw our results from that. There are 12 people in here. Everybody roll your dice once. Just roll it.
2.
Okay. Raise your hand if you got a 1. Raise your hand if you got a 2. Raise your hand if you got a 3. Raise your hand if you got a 4. 5. And 6. Okay. So let's say that was equivalent to rolling the dice 12 times. Okay? So if we do our probability distribution based on this, how does that compare to these? Can someone grab your calculator and just do, really we just need 2/12, which that's a 6, so that's 17%. Never mind. And then 3/12 is 25. Okay. So the 5 came clear up here, and all the other ones were here. Okay. What do you notice? Did any of our hundreds look anything like that? Any of our 100-row graphs look anything like this?
One of
No. Go ahead. Yeah, it's completely missing, right? And the 5 is a fair bit higher. So did any of our rolls of 100 look anything like that? Okay. Let's do just this row, like Cooper's row over. Everybody, you guys roll.
No statements.
What is the problem with this?
Did you break your
I think I did break it.
Just click on the drawing one.
Like where? How come my bars are not showing up?
one equal one.
I
Okay.
think like the more you do it, the like more likely you are to have a theoretical something happen.
Okay. I like what I'm hearing. So the question was, again, what are we getting at by doing this obnoxious thing that I'm doing right now?
A laugh.
Yeah, just laugh it off. Give me a break. There we go.
There's some.
How about we all get a break?
No, be careful not to hit the backspace bar.
Okay.
How about we all just
So comparing 12 rolls, 7 rolls, and then 100, what are we getting at? Like these look different. We're missing a complete number, or one is vastly different. We have some that are kind of normal. But then as we get up to 100, it's starting to look a lot more uniform, right? Everybody's was similar. What if we had all rolled it 1,000 times? What would you expect?
Very, very
Well,
similar.
like they would all be like.
Okay.
21 off,
Okay.
I'm guessing.
So thinking that,
You know, honestly, now I kind of want to do that.
That we roll it 1,000 times and we miss like the whole 3 columns.
Honestly,
well, what do you think the probability would be? Not a number, but just conceptually, that we could roll it 1,000 times and never get one of these numbers.
almost impossible.
We all rolled it 100. We could just add all those together and get the average of like 1,000.
That's true.
True.
But
That's a good point.
one of us, we all got all of the numbers.
And there was at least 10 of you doing this yesterday, so we have at least 1,000 rolls represented. So this is something called the law of large numbers, which is basically exactly what you said. The more times that you do an experiment, the closer the probability gets to the theoretical. Yeah. And we're kind of seeing that.
How about we
So
roll it
let's
a
kind
million
of,
times?
let's put that little idea in your note. And it makes sense. I think it makes sense,
Yeah.
right? Like if we roll the dice 2 times, maybe let's just do 6 times, it's entirely possible that we would never get a couple of the numbers. Like you've all played dice games, right?
And for the first little bit, I was rolling to get a 4.
Yeah. And like, so think of one like Yahtzee. And you can sit there and have your turn go around and around and never get the one you want, right?
Oh, yeah.
Okay? But if we'd sat and played it for 24 hours rolling the dice, we would definitely get all of those things. Okay?
How is this in the theoretical possibility of getting 1 through 6
Uh-huh. And how'd it go?
Not good. I went 3 tries and didn't get it.
Okay? Well, there you go.
Like 1 through 6 and 6. No, 1 through 6. What? We don't have that extra space there.
It's just at the bottom, underneath. Yeah, you do. You have
Yeah.
the,
Large number committee.
you have space after
no, I
that.
already, oh.
It's at the end of the one we wrote yesterday. Okay, as the number of trials being like each time you roll, or experiments, however you want to call it, as that grows, the experimental probability approaches the theoretical. Alright, so there's a specific distribution called binomial probability, binomial distribution. And I've talked about this a little bit, but now we'll get into it and give you the formula for it. So if we can narrow down our choices, our outcomes to something we can term a success or a not success, then we can use this concept of binomial probability. Okay? So you have three conditions that have to be met for that to be usable. Like I said, each trial or each experiment has two possible outcomes. One that we call a success. And don't get caught up in like success failure so much as, hey, if I roll a die and I want it to be an even number versus an odd number. Like that's two different things, right? So that's success would be I rolled an even and odd number would not. The results are independent, meaning that one doesn't affect the other. So each roll of the dice doesn't affect the next one. And then the probability is the same for each trial. So those three conditions have to be met. And if they are, then we can boil this down a lot simpler to binomial probability. Will you grab the combinatorics worksheet that we had? We just had like paragraph problems on front and back. Yeah.
Okay, so if you're trying to get one for 6 and one in 6 rolls, would that be a binomial experiment? Because I could have a paragraph for them.
Okay. Will you ask that again? And so, rolling dice, or just one, I guess you're saying, right?
Yeah, and like trying to get the numbers 1 through 6, not in that order. In
Oh,
6
okay.
rolls.
Just get each number?
Yeah. Would that be independent? Because, or would that be conditional?
No. Why would it be conditional?
Because you can only get one number each time. So like if I already got one, then I can't get it again.
You can get it again, but you just can't count it again. Like it still will come up.
Okay, right.
So the probability of the number 1 coming up won't change.
Oh.
It's just whether or not you consider it in your tally, right?
Well, but I only have 6 rolls.
Oh, only in 6 rolls?
Yeah.
You probably should have just left that on the floor. Is this a binomial experiment?
I don't know.
Well, let's kind of analyze. Does each trial have 2 possible outcomes?
Yeah. Well, no.
I'm rolling it 6 times, 6 trials, right?
Yeah.
Does each one have 2 possible outcomes?
Oh, you're gonna
Okay. Yes, it has 6 numbers, right? Each roll has 6 numbers. But can we say it's a success or a failure?
Yeah.
Okay. The results are independent. Does the probability of success, is it the same for each roll?
Yeah.
So I think this is where this would break down because of what you said about it has to happen in 6 rolls. And then you said, I think it is conditional, right? Because if I roll and I get a 5, then 5 is checked off the list as a success, right? It no longer gets to be counted as a success. So now my next roll, I have still 6 options on the die, but I can only consider 5 of them a success because I have to kick off the 5. So that changes the probability of success now. Does that make sense?
Oh, yeah.
Wouldn't the first trial have no failure?
And the first trial has no failure. Good point. Because any of the numbers would be okay to start with. Yeah.
So the answer's
So this is not binomial. Okay, on the sheet that I just had you pull out, look at number 3. So we did this one with combinatorics the other day. But read it this time. A fair coin is flipped 10 times. What is the probability of the coin landing heads up exactly 6 times? Could we do this with binomial now?
Yes.
Okay, so let's analyze the 3 conditions. 1, can we delineate success or failure?
Yeah.
Yes. 2, are they independent each time I flip? Yes. 3, does the probability of success change as we flip?
Yes.
No. So we could change. We could have it done this one with binomial probability. So leave that sheet out, and we'll come back and do it that way. And I think you'll find it conceptually a lot easier than the way we did it. In fact. Also, look at the next one. How about it? Can we do it with binomial probability? So again, can we delineate success or failure for each trial? Yes, it's either even or not even, right? Success is even, and then, so success is even, and then odd would be not a success. 2, are they independent? Does one roll affect another?
No.
So they are independent. 3, does the probability of rolling an even number change each time? No. Okay? So, again, keep that sheet handy so we can come back and work that with binomial probability and see which one you like better. And as usual, it doesn't actually matter to me once you get into this which way you do it. All right. So let's look at this spinner. It says it's spun 3 times. Assume that the spinner is equally likely to stop in any of the sections, meaning the mechanics of the spinner aren't, there's not like a sticky spot or something. Success is landing on a section marked go forward 2 spaces. And it's, if it's hard to see, here's one. No, that's it backward. That's forward. Here's forward. Okay. So is this binomial?
Yes.
Do you feel like you need to write the conditions down so you can look at them? These three things? You want to write those first so you have them? Okay. Okay, so first condition is that you can, I don't know what word to use, I keep saying delineate, but let's say describe one outcome as a success. I guess we could say, and the other not. 2, the trials or events are independent And then 3, the probability of success. Each time, each trial. Does not change. We'll come back and do an example, but just have those for reference while we kind of learn how this looks. Okay. So again, our success is landing on one of the 2 I marked with green arrow. So, is this a binomial experiment? Can we delineate success failure? Yes, it either lands on there or not, right? Does that mean the probability is 50-50? Okay, so this is what I was talking about yesterday. Just because we're saying success versus failure does not mean 50-50. So be careful with that. All right, yes, we can call 1 a success. 2, are the events independent? Does one spin affect another spin? No. 3, does the probability of landing on one of those 2 change with each spin? No, it's the same. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So 1/4, 2 out of 8 each time. I have a 2 out of 8 chance. Okay, so that's a binomial experiment. Yes, it meets the criteria. In a class of 23 students, 7 students completed the term project. 2 students selected at random have to give presentations. Success is that the student has completed the project. So let's make this clear. If I picked out of you guys, 7 of you completed actually completed the project, and I picked 2 of you at random to present. So is this binomial? Can we describe an event as a success or failure? Which is what? Like, what's the description?
Did it work?
Yeah, did the project or not did the project. Okay. 2, are the events independent? Does Audrey doing the project affect if Tom did it? Probably not. Unless you're like best buddies, it probably doesn't, right?
Unless it was like a paired.
Well, that's true, but it's kind of worded like this is individual.
Yeah, because 7 is not an even number.
Well, because if it's a pair thing, you would have to say, yeah.
Yeah.
Okay, so let's assume it's independent. And then does the probability of any one student having done the project change? No. So is it binomial? Yeah. Okay, don't worry about how you're going to calculate it because it's a little complicated sounding, but it isn't too bad. All right, last one, maybe 2. Select a card at random from a set of 7, 4 labeled A, 3 labeled B, and then you select another card from the cards that remain.
Nope.
Is this binomial?
No.
No, because you didn't put it back.
So which of the 3 criteria does it fail?
Success rate. The probability of success.
And I guess technically it's not independent either.
Yeah.
Okay. If you roll a standard number cube, so roll a die 4 times, assume that each time you roll the number cube, each number is equally likely to come up. For each roll, success is getting an even. So that's kind of like number 2 on our, number 4 on our sheet. What do you think? Is that binomial?
Oh, yeah.
Can you call a success or failure? Yep. Are the events independent? Yep. Does the probability of success change? Nope. So yes, this is 1. Okay. No bells, remember, so let's take our break for a few minutes. So please keep an eye on the time. Just be gone like 3, maybe 4 minutes. So here's the formula for binomial probability. Okay, so let's look at it and then we'll talk about how to use it. Basically, anytime you have a formula, I told you this, it's easier math because it's just plug and chug, right? Make sure you get everything plugged in right and then chug through to get your answer. So here's again, the way it looks, probability of our successes. So ways to get our successes. It's the number of successes. And if you look at this, it sort of starts to make sense. We've seen NCR before. What is that? Well, it's this first description. It's the number of ways that you can get however many successes you're looking for. Okay? So number of ways. And this time, N is the number of trials that you're doing. Okay? So if we did the dice thing, if we rolled it 50 times, then we're doing 50 trials. That's our N number. Okay? This P to the R, so probability of getting our successes. Think about, if you remember, if I said how many ways, just as a reminder, why it has an exponent. How many ways can I flip a coin 10 times? What did we do for that?
We're gonna do 2 to the power of
2
10.
to the 10. Okay, same idea. The probability of our successes means that I have to do that, whatever the probability is, let's say for this it's 50-50, I have to do that many times in a row. So 2 to the whatever power. That's this little P to the R. Okay, just ignore everything else in here. If P is the probability of success, what is 1 minus P? Yeah, that's the other probability, right? So the probability of not getting a success, and that's to the N minus R. In other words, let's just get rid of all that scribble. If this is the probability of getting success multiplied out however many times we hope to get a success, this is the probability of failing multiplied out however many failures that leaves, okay? So if we say roll a die 10 times, and how many times will what's the probability of getting a 4 3 times? Okay? So let's just kind of talk through the numbers. What is N?
10.
It's 10. It's 10 rolls. So 10 trials. What is R? How many times do I hope to get success? 3. So getting a 4 3 times. So this would be 10C3. What's the probability of success? What's the probability of rolling a 4? 1/6. So 1/6. R times, how many times do I hope to get that?
3.
Okay. So there's my probability of success. 1 out of 6 each roll, and I hope to do it 3 times. Remember that as we do things more, the probability goes down, right? Meaning, let me rephrase that. And probability makes it go down. I want to do it once and twice and again. That means the probability should go down. Okay? Anyway, what's the probability of not getting a 4? In other words, a failure. 5 out of 6. And how many times will that happen, or am I okay with that happening? 7 times. Okay, and then you just multiply all that out. And that tells you the probability of rolling a 4 3 times out of 10. Okay? So there's some details that you have to pay attention to and make sure that you fill in your formula correctly. But after that, it's nice. Okay? so it's not confusing. Let's go put the formula down here. It looks a little ugly, but I think once you've talked through it, it's really not. Kind of makes more sense.
Hey, unit has
Let's make sure we define all the terms. Now, you saw me in there put the probabilities as a fraction. What would be the other acceptable way to put it? As a decimal, not as a percent. So, let's say that so everybody's clear.
Does the n say n minus r or n minus 1?
R.
Okay.
Correct. And I hate to keep saying the word failure, but it kind of stands in opposition to success, so it makes sense. Okay, I'll let you catch up filling all that out. Okay, so what should you do first?
Finish writing this.
Yeah. You do need to make sure that the binomial situation actually applies.
We need to like underline all those keywords.
I don't care. If it helps you, underline them.
Did you write the number 1 and then say first?
Yes, I sure did. Why is that a problem?
Well, wait.
That should
First,
be
It's
illegal.
redundant.
Yes,
1 first. Yeah, okay. It's fine.
I believe that should.
Is this binomial? Well, go through the 3 conditions. Is there a success and a failure?
Yes.
What's the success?
Heads up.
Flipping heads,
Exactly.
okay? Is it independent each flip?
Yes.
Does the probability change?
No.
No. It just doesn't change enough to actually.
Okay, step 2, I should have written that in pink, hold on.
I'm already writing it in pink. Don't change it on me.
Alright, next step. I want you to write the equation, the formula every time. Write it out and identify N, R, and P. Those are the 3 main things you have to identify. What is N?
The number of tries.
Wait, did you put 2 second? Oh, you didn't.
Such you patient.
Okay, so N is 10. R is how many? 6. P, what's the probability of flipping your heads? Yeah, so you could either write 1/2 or 0.5, either one. Okay. And then we fill out the formula, so P of 6 heads out of 10. 10 flips. Please do get in the habit of writing in the parentheses what you're trying to figure out. So 6 heads out of 10. So 10, and we're trying to get 6. So 10C6, and then you'll want to use lots of parentheses on this. 0.5 to the 6th times 0.5 to the 4th. And you guys, if you want, you could add over here, you could say 1 minus P is 0.5, N minus R is 4. So then you can just plug all that in. Okay? That would be a nice organized way to do this. I said you could write these two as well, not just N, R, and P, but those two. Then everything is just ready to shove into the formula.
There's also 1 minus P.
Yeah, it says 1 minus P.
Is also the same as P.
In this case, because P is 0.5. That's the only case where that will be true. Right?
Yeah.
Literally any other number for P will not be the same for both of those. So most of your problems, those two numbers will not be the same.
So look, if it's 0.6, the other one would be 0.4.
Yeah. Right? Because the probability of success and not success is the same for flipping a coin.
So I think the one was just wrong.
Well, that's 100% probability. So if I'm taking away the probability of success, then the rest of it is failure.
Oh,
That makes more sense.
Okay. And then we just carefully enter all of that into the calculator.
That's too much calculation.
No, you're gonna have to go back.
Yes.
See, too much calculation.
Oh, it's just, I don't know why calculators do that. It always bugs me. 0.5 to the 6th. Go down. There we go. Times 0.5 to the 4th. Enter. 0.2, let's say 0.205.
That's the same thing we got on the other one.
Yeah, so again, if you go back to the way we did it with combinatorics, I think this way that we did it before was a lot more confusing. Do you agree? You're welcome to do it that way though. And then 105 out of 512 is the same percentage as what we just did. So the entire number is exactly the same. So either way is fine. Pick your favorite way. But definitely it's,
The easiest.
I think, more confusing to do with combinatorics. Okay? Be careful that you don't apply this formula when it's not a binomial situation. In fact, go back to that sheet again, and let's just look at one of the other ones that we did. Like, look at number 1. Is it binomial?
no.
Or number 2. Could we have done that with binomial probability?
They wouldn't have been right, but theoretically.
Yeah, I think you could with this one. You're picking 10 out of the 14, and you could say success is no information given to the spies. So success would be not having a spy. Failure would be having a spy.
Which is almost impossible.
So I think you could do it that way. I think number 1 would be weird to do it because it's I don't know, for me it is at least. So now you have more tools in your toolbox. Everybody good with that? Let's just work for a bit.